Hello, and welcome to Lecture 11 of AMAT502 at UAlbany. Today, we're going to go over some of the basics of probability theory and the distributions of random outcomes. Hopefully, most of this is a reminder to you, but I want to go ahead and provide some context and a little bit of a refresher for you. Topics for today are going to be a broad overview of the difference between determinism and randomness. We're then going to specialize this discussion to the case of programs, specifically those written in Python. We'll remind you of some of the elementary rules for calculating probabilities and discuss how this relates to experiments and what we can actually do in a computer, which sometimes goes underneath the heading of the Frequentist approach to probability. We'll conclude with just a few examples of some common distributions that you should be aware of, which we'll pick up in the next lecture. So broadly, we like to think of most of the universe as being deterministic. What that means is that if you know all the specific details and you know that the laws are not sort of chaotic, even though there's a difference, some things can be deterministic and still chaotic. But if we can predict using laws, such as Newton's laws, then we can understand the entire course of history. The most simple example of this is, for example, if you know how to throw a baseball and you know the velocity, which tells you both the direction and the speed, then the Newton's laws will tell you exactly how the baseball is going to fall. Of course, this picture here might remind you of something you've done in elementary calculus. Essentially, you're solving a very simple differential equation, which governs the body motions of bodies, such as the planets. Now, for the longest time, scientists really believed that the universe was fundamentally deterministic, and that, in fact, with Newton's laws in place, we could predict the future. Again, there are several reasons why that's not entirely true. First of all, small influences can accumulate and create unpredictability, even though the evolution of events is deterministic. But more recently, in the 20th century, we had this revolution occur where quantum mechanics seemed to suggest that at nature's most fundamental level, things were actually random, and that, in fact, these couldn't be explained just via missing or hidden variables. So let me go ahead and just give you a brief review of how this happened and what quantum mechanics says. So instead of looking at the motion of, say, bodies like baseballs and the planets, suppose I'm interested in things at the atomic level, the very small level, like the hydrogen atom. The framework that we've developed to explain how the hydrogen atom and other basic elements work is that essentially these objects have a finite number of states. For those of you who have taken some linear algebra or possibly taking functional analysis now in preparation for machine learning, the accurate way of saying this is that states correspond to eigenvectors of certain measurement operators. And that's really the fundamental perspective of quantum mechanics, that reality is governed by what is measurable. So things like energy and position and momentum, or even this notion of spin, each of these are defined as operators, which operate on the space of possible states for some of these atomic objects to be in. And the surprising fact is that there are only discretely many of these states or eigenvectors, which means that they're kind of quantized, i.e. that there are only a limited countable number of possibilities. Now you might ask, why is that possible? The example I like to tell everyone about is, well, this is actually a very familiar concept in wave mechanics. So if I have a vibrating string, we know that there's something called the fundamental mode, which is where the string just oscillates up and down. By contrast, you can sort of double this and look at higher modes. So this means where the rope oscillates around some fixed midpoint. And then you can get these higher vibrations where the string oscillates around 3 points with these two fixed midpoints. And in fact, this is what explains pitch and some of the frequencies that are pleasing to our ears, sometimes called harmonies. And in fact, this is why we have the term that you may have heard from calculus, the harmonic series, because this measures how you divide your interval, your rope length, into parts where it can oscillate. So I have, here's 1, and then here's a half, and then here I've divided my interval to a third, and then I've divided my interval to a fourth. And these are higher and higher. So these are examples of a discrete number of states. Now, the basic idea behind quantum mechanics is that if I instead think about a rope that's on a circle and oscillations of this circle, this is actually what we believe is the best explanation for how an electron moves around the nucleus inside of the atom. And you'll notice that because we can't allow this sort of mismatch to occur, because this would sort of cause destructive interference, there are only so many finite number of modes that electrons can have in the atom. And this is where we get all these things like shell numbers and so on and so forth from chemistry. Essentially all of chemistry and quantum mechanics you can think of in terms of wave mechanics. Now, what is the fundamental hypothesis of quantum mechanics? It essentially says that everything is a superposition of these different states. Superposition is just a fancy term for a linear combination. And in fact, if you know a little bit of history, the Copenhagen interpretation of quantum mechanics says that all of reality fundamentally exists in the superposition of these various states until we observe it. And what observation means is applying one of these measurement operators, at which that point our system jumps to one of these finite number of states. And that means it collapses onto one of the eigenvectors of this operator. And the probability that it jumps to one eigenvector or the other is determined by the coefficient, which has complex coordinates. And so this is essentially where evidence that reality at its most fundamental level, at its atomic level, is random. This process of jumping from state to state between observations is the basis for randomness in our world. Of course, you might think this only applies to things at the small level, but Schrodinger had this very famous thought experiment known as Schrodinger's cat, where he imagined that there was a hammer that was tied to a little device that just basically observed whether or not a particle decayed or not. And we know that for some period of time, the probability of decay, it's a random outcome. Maybe it won't decay, maybe it will. And so if you really took seriously the implications of quantum mechanics, it would say that the cat inside this box exists in a linear combination, i.e. a superposition of the state of being alive and dead. Okay, so that's enough about context. Let's go ahead and describe how this shows up in mathematics and in Python. So first of all, most things in math, we'd like to think of as deterministic. Functions mathematically are deterministic. If you give you an input, you have a well-defined output. So when we try to implement functions in Python, we expect them to also be deterministic. So for example, earlier, we implemented the square root function using bisection search. Let me just go ahead and remind you of how that looked. So here I have the number I want to take the square root of, and I go ahead and I have e here. Now this should actually be max of x and 1. And I'm hoping that when I perform calculations of the square root of 2 with a fixed value of e or epsilon, I'll get the same output. So let's go ahead and try that. Indeed, I ran this function 4 times, and for each of those 4 runs, I asked it to print the output. And from what I can see, I got the same output. This is an example of determinism. And so this program is fundamentally deterministic, subject to its implementation. So how might I write a program that is stochastic? Stochastic is just a fancy word for unpredictable. meaning that its outcome is described by some probability distribution. So for example, suppose I wanted to write a function that every time I invoked it rolled a fair die. You know, a die, cube, has 6 sides, has numbers on it. So that means every time I roll it, I want to get an outcome. How would we do it? If you just had the very basic operations of Python, it's not very clear how you would do that. And in fact, we have to rely on packages that were already written, which invoke very complicated notions of pseudo-randomness, because really fundamentally in the computer, it's hard to, you can't really have true randomness. I could say a little bit more about that later. Now, last lecture, we already introduced this random int function, which we used to create NumPy arrays, which had entries that were populated according to some list of possible values. So let's go ahead and invoke this random int function, but built inside of this other function, roll die. So notice if I run this again, I have 513, 3146, etc. I could also do it again, I get a different output. So this means even if I have the same code and I run it multiple times, I get different outputs. That's an example of stochasticity. It is a stochastic program. All right, so let's try to tie some of this with some things we should know from basic probability. So obviously our output seems random in a certain sense. So let's do a conceptual question. Would it be more or less surprising to instead see the output where our list consists of all ones, meaning every time we invoke the roll die function, we got a 1? Is that more or less probable than the string we just got back here? This array we got back here, 5, 3, 5, 4, 1, 4, 4. If I do it again, or is it more likely or less likely than this string? Well, the answer is actually that neither one is more likely than the other. In fact, they are equally likely. And that has to deal with the fact that each roll, we believe, is independent from the other one, which that means is that the value of the first roll doesn't affect the value of future rolls. And in fact, if you just think about how the world operates, it seems plausible that it would be hard to tell a causal story that connects the roll of the die at one time to the roll of the die at the other time. So let's get into some language that should be familiar from your probability courses. So we like to talk about the probability of events. An event is a subset of the space of all possible outcomes. In the case of roll the die, it's a subset of the possible outcomes of rolling a die, which we know 1 through 6 are the possible outcomes. And sometimes in discrete probability, we like to focus on things where every outcome is equally likely. This sometimes goes under the heading of equal likelihood statistics, or even just what's called the uniform measure. So what that means is that if I want to know the probability of an event under the assumption that every outcome is equally likely for a discrete random variable, then all we have to do is just count the fraction of states that have a certain property specified by the event versus the space of all possible outcomes. So let's do some examples. What's the probability of rolling a fair 6-sided die and getting the value of 3? Well, our space of possible outcomes is 1 through 6. We assume every roll is equally likely. And so the only way we can get a 3, well, there's only one possible way of doing that. So that means the probability is 1 out of 6. Suppose I wanted to know the probability of rolling 2 3s. So I maybe have 2 die and I roll both of them. Well, in this case, I can coordinatize the space of possible outcomes using pairs, coordinate pairs, tuples, 1 through 6 possible outcomes for the first entry of the tuple, 1 through 6 possible outcomes for the second entry of the tuple, which means that we have 36 in total possible outcomes. And so the probability of rolling 2 3s is 1 out of 36. So those are examples of outcomes. Events, remember, are collections of outcomes. So what's the probability of rolling an even number if we just roll a single die once? Well, there are 3 states that are even, 2, 4, and 6. So the probability of an even outcome is the size of the set, which is 3, divided by 6. I'll leave it to you to try to figure out what's the probability of rolling 2 fair 6-sided die and at least one of the values being even. So that means first roll could be even, second roll could be even, or both could be even. All right. I apologize. There's a small typo here, which I'll fix. So independence fits well in what's called the multiplication rule. Notice that if I want to roll a 3 and roll a 3 again, that probability is 1 over 36, which is the same thing as 1 over 6 times 1 over 6, which is the probability of rolling a 3 times the probability of rolling a 3. So the fact that I was able to turn this and statement into a multiplication is a version of independence. Additionally, there's the rule of complements, which says that if I want to know the probability of an event not occurring, so that means it's the complement of an event, meaning the complement of the subset of the space of possible outcomes, I just take 1 minus the probability of that event. Which makes sense, because if I bring this minus PA over to the left-hand side, then the probability of A or not A occurring has to be 1, because there I've defined all possible things. Either A occurs or it does not occur. It's not possible for one of those 2 statements not to be true. All right, so you might also consider the question, what is the probability of rolling a fair 6-sided die 25 times and never rolling a 1? Well, again, assuming independence, I can just turn this into the product of probabilities. Not rolling a 1, not rolling a 1, 25 times, which is 1 minus 6 raised to the 25th. Sorry, cuts off. And now, all of these calculations were just instances of probabilities I told you, and then I also declared that certain things were independent. But where did these probabilities come from? How do we know that actually the probability of rolling a 3 is a 6th? Basic question is, what if we're out in the world and we're being scientists and we're actually observing rolls of die? How might we actually calculate probabilities? This is tied very deeply with the question of, how do I know a die or possibly a coin is fair or not? Meaning, fair is the same thing as every outcome is equally likely. So here we want to use the notion of inferential or frequentist statistics, which means we want to infer what the true probabilities are. And we're going to do that by computing examples a bunch of times and then just counting the frequencies. So the guiding principle of inferential statistics is that when we draw a random sample or perform an experiment, we expect this to be, in the long run, sort of representative of the process or population that we're drawing from. So let's do an example where we computationally figure out the average number of rolls as we roll it n times, or average number of outcomes for each outcome as we roll it multiple times. All right, so we've now defined our roll mean function. So now we're going to go through each of the possible outcomes, 1 through 6, and then we're just going to count instances of that outcome, and then divide by the total number of times that outcome was observed. So let's go ahead and roll our die 100 times and then look at the frequency of each of the possible outcomes, 1, 2, 3, 4, 5, and 6. Notice that was very quick. And contrary to what we just said, the probability is very evidently not a 6th, because each of these things are different. And we know that when we add up these 6 possible frequencies, we should get 1. That's 100% of all observations. That's here I'm using the Frequentist language. So let's go ahead and roll our die 100,000 times and calculate each of these frequencies. Notice that we're seeing things that seem to gravitate much more closely to the same value, which is increasing our confidence that actually this is a fair die that we're rolling. And in particular, that these frequencies are tending towards the true probability of 1/6. What we're witnessing in action is something called the law of large numbers. And essentially what this says, and sometimes people say the law of averages, is that as the number of trials or observations increases, that's n, then the average value of the sample tends to the true probability of the event. So let's use matplotlib to try to visualize some of these frequencies as we roll our die increasing numbers of times. So here we've defined a law of large numbers function. I'll leave it to you to read the implementation details of this function, but let's go ahead and see what happens when I roll my die 1,000 times. You can see that happens because I've invoked this function with n equals 1,000. All right, it's rolling, it's rolling. All right, I got something, and of course it's my first iteration, so it didn't quite plot, but when I ran it the second time, it did. So here what we see is that when I look at the frequency of, counting the number of times that we roll a 3, early on we start off with even half of our rolls being 3s, and then this value oscillates, but the values of these oscillations get smaller and smaller and smaller. And in fact, we can give precise answers for how this band of probabilities evolves. And what I've also plotted here, this red line, is just corresponding to 1/6. At least it's carried out to a few decimal places. So what you want to think of this is as essentially a probability distribution. So in the limit, we're assuming that each of our outcomes, and here we think of x as a variable, varies between the values of 1 through 6. And the probability of each of these possible values appears to be converging on a 6th. So this display, this table right here, sometimes called the probability mass function of a random variable. And in this particular instance, because all these values are the same, we call this the uniform distribution. That means each outcome is equally likely. And usually when we say pick a number at random, what we're saying is choose a number according to a uniform distribution of probabilities on the choices that exist. Now, computationally in Python and in mathematics in general, we have a way of visualizing these sorts of probability tables. This is really what's called a histogram. And so you can think of a histogram as being the tabulation of outcomes according to a certain number of experiments, which express what's sometimes called empirical probabilities. Being empirical means you observe something. So here we are observing the number of frequencies that a given outcome occurs when we've done an experiment n times. So let's go ahead and look at some histograms. And again, we get to use some of our features from random library, and we get again use our hist function, which again we used last time. So let's go ahead and look at what we just did. But what this function is actually drawing from is it's drawing from a normal random variable. So that means that I'm taking 10,000 draws from some random variable where the underlying distribution is governed by something called a normal distribution, which we're going to go over soon enough. But whenever we tabulate these outcomes, we get this, again, bell-shaped curve, which is now spiky because we are cutting off a range of possible values. But again, it still has the same general shape. If I run this again, you'll notice some of the heights change. Let's try to do that again. Again, now that those heights are very different. But either way, we've binned our outcomes, and this is all graphed using a histogram. All right, so we need to cover a little more detail. So earlier we assumed we had a discrete number of outcomes, like rolling a die 1 through 6. But in fact, what we often see in the real world and with data is we see values which are continuously varying. So that means we have a continuous random variable. So when we have a probability distribution that's discrete, we can use one of those tables, and we use the language of a probability mass function, which governs the probabilities of each of those discretely many outcomes. On the other hand, we have continuous random variables. Like think about the height or the weight of a person. And you can't predict it. You look at a person, they're going to have different height or weight, even on different times of the day. The distribution evolves according to what's called a continuous distribution. We use the language of a probability density function. One of the key differences of probability density function is that if we want to know the probability of an individual outcome, like what's the probability that someone is 5, 8, and 3/4, it's essentially 0, because very few people are exactly that height if we carry out to infinitely many decimal places. Instead, what we do is we take a window of tolerances of someone's height, and then what we're doing is computing the area under the curve of the probability density function. And so probabilities for continuous random variables are computed using integration. So let's go over some examples of discrete and continuous probability distributions we haven't yet considered, but which you've hopefully seen before. So let's go back to our rolling dice example. There we see that we've got our die, and the possible outcomes are 1 through 6. So the underlying distribution of rolling a given value k times, when you roll die a total of n times, needs to have some discrete distribution. You know, again, if I roll a die 3 times, it's possible that I'll get the value 3 all 3 times. Or maybe I'll get a 3 on the first roll and not on the second or third. But notice there, if I'm rolling a die 3 times and I'm asking for the chance of getting a particular value, I could get it no times, 0 times. I could get it 1 time, I could get it 2 times, I could get it 3 times. That's 4 possible values. So now if I were to look at the chart of probabilities there, what would I get? So we can, again, use the rules of probability to actually compute this answer precisely. So what we're really knowing is what's the probability of it rolling, let's say, 2 1s. So here I'm asking the outcome to be 1, and I want it to happen twice when I roll it 3 times. So that means I could, roll a 1 on the first roll, not roll a 1, and then roll a 1 on the second roll. Or I could get a roll on the first one, roll a 1 on the second one, but not on the third. Or I could not get a 1 on the first one, and then the next 2 rolls are 1s. So those are 3 possibilities. So notice that this is going to be different. So we have 3 possibilities, but now we need to compute the probability of each of those possibilities. So here we get to use independence and our rule of complements. So if we denote rolling a 1 as a yes, so yes, we got a 1. And we roll anything that's not a 1 as an n. So we negate that. It's not a 1. Then the 3 possible ways I just described is we could get yes, yes, no, or we get a yes, no, yes, or no, yes, yes. So it's a 1, 1, not a 1, a 1, a not a 1, a 1, not a 1, a 1, 1. Okay, now let's compute the probability of each of these individual outcomes. Well, using independence and the rule of complements, we know that it's a 6th times a 6th times not a 1, which is 1 minus a 6, which is 5/6. So I have 5 divided by 6 to the 3rd power. So that's our probability of any one of those individual sequences of yeses and nos. But there were 3 sequences, and each of them are equally likely. You could just see that by changing where the 5/6 is. But since multiplication is commutative, you get the same number. So I need to add up all the possible ways in which that outcome occurs and the probability of each of those outcomes. This is sometimes called the law of total probability. All right, so notice that this 3 is also the same thing as 3 choose 2, which means I have 3 possibilities. I want to choose 2 of those possibilities to be where the 1 rolled. And so that's 3 factorial divided by 2 factorial divided by 1 factorial, which gives us 3. So 3 times the probability of a success, yes, times the raised to the number of successes power, and then the probability of failure times the number of failures, raised to the number of failures power. Again, this is just telling us we multiply that number of times. That is expressing independence. And so this is all collated in the following distribution, which is called the binomial distribution. Essentially, this asks if I have a process that's I take in trials of, and for each trial, I either have a yes or a no. A yes with probability p, or a no with probability 1 minus p. And I want k yeses, so that's the number of successes. And then consequently, since I'm only doing it n times, n minus k failures. And the probability of that outcome is n choose k, because I have to choose the k locations for my successes out of my total of my n trials, times these probabilities, which I computed using independence and the law of complements. And because this coefficient right here is sometimes called the binomial formula, or is computed using, is what appears in the binomial formula, we call this the binomial distribution. It's an important one to remember. Now, I want to consider an example of a continuous distribution. And I already alluded to examples of continuous random variables. One of those is, say, the height or weight. Now, normally when we look at a particular population, let's say men in the United States, there's an average weight, which we think of as mu. And there's some variance or variation, which we measure using something called sigma. Sigma is our standard deviation, and so variance is sigma squared. Then the probability density function, the PDF of a normal distribution, is given by 1 divided by sigma, that's our standard deviation, times the square root of 2 pi, times e to the minus x minus mu squared divided by 2 sigma squared. We'll plot this and you'll see that this looks like our familiar bell curve. Now, in the situation where mu is equal to 0, that means our average is 0, and our standard deviation is 1. We'll call this the standard normal distribution or the unit normal distribution. All right, so there are a couple of ways in which we might get this. So let's go ahead and use some variables. Mean mu, standard 1. A variance is going to be squared of our standard deviation. And let's go ahead and use our A range function where we take decimal steps. And then I can just call f and use np.x. That's the numpy's shorthand for the exponential function. And then I essentially write the equation I just showed you, but now in Python. And so if I want to plot x and f of x, so that's f applied to all these values x, I can do so. And you'll see that I get this familiar normal distribution or bell curve. Now, I already alluded to the fact that probabilities for continuous PDFs are computed using integration. And so one thing which I want you all to remember, be aware of, is some of the standard values for integrals under the curve, or the area under the curve for the normal Gaussian curve or normal distribution. In particular, what happens when I integrate from -1 to 1, or -2 to 2, or -3 to 3? Each of these, you can think of these as measuring the number of standard deviations from the mean. Again, that's sort of distance from the mean. Now, I encourage you to read through the code that actually plots the function I just showed you. So in fact, if I run it, you'll see I get exactly what I just showed you. And here I've gone ahead and done some tricks where I've filled the area between certain values, which is, again, it's a useful visualization trick. Now, one of the core things I hope you remember from your probability and statistics course is that there's special values for the area under the curve when I go from -1 to 1, -2 to 2, or -3 to 3. Essentially, this counts the frequency of outcomes that are within 1 standard deviation of the mean, 2 standard deviations of the mean, or 3 standard deviations of the mean. That is 68% of all observations of a random variable occur within 1 standard deviation of the mean, which means that, for example, if the height of an average man in the US is 5'9", standard deviation of 2 inches, then 68% of the time you'll meet people that are within 2 inches of 5'9". Or if you want to count for 95% of your observations, you need to go 2 more inches. So that's going to be 4 inches above and below 5'9". Or maybe you need to go 6 inches out, and that's going to account for 99.7% of all observations. So that means that when you're watching some of these guys in the NBA who are almost 7 feet tall, some of them are over 7 feet tall, you're looking at a very, very, very small percentage of the population. And you can actually quantify just how rare that is. All right, that's it for today. I wanted it to be a short lecture so we could do some more exercises. And I look forward to seeing you all in class.